representing complex numbers geometrically. This is where we combine our last topic with this topic, and it also explains why we did vectors as the last topic, to help us with this. Complex numbers can be represented as vectors. So there's our Argand diagram. There's the point z equals x plus iy. Join it up to the origin, we now have a vector. But the advantage with vectors, as we've seen, is we can move vectors. And it doesn't matter where I put it, I can put it down there. Head minus tail will still give us the same answer. So it still represents the same complex number. Or I can put it over there, and again, it's still the same complex number. So it does not matter where we move that vector to, its length's going to stay the same, so the modulus is the same, and the angle it makes with the horizontal will stay the same, so its argument stays the same. Remember, if ever you want to work out the complex number, head minus tail. Exactly the same as vectors. So how do we add and subtract? Well, this should be no surprise then. There's one complex number, z1. There's another complex number, z2. So if I want to find z1 plus z2, we add the vectors. So head to tail as we do. We end up with the green vector there, z1 plus z2. And of course I could have done z2 plus z1 gets in the same position. Now to subtract, we saw that, well, we add the negative vector. So I'd end up down there, z1 minus z2. So that would be the black vector. Well, that's the position vector. But I can move it, and conveniently, I'll move it there. Head minus tail, z1 minus z2, it's still the same complex number. So all those things we saw when we're looking at vectors, we get that parallelogram. One diagonal is z1 plus z2, the other diagonal is z1 minus z2, or z2 minus z1, depending on the direction of the vector. Now this brings up an interesting point. There's a little thing called the triangular inequality, and it's kind of obvious when you look at it. In any triangle, a side of a triangle must be shorter than the sum of the other two sides, because the shortest distance is always the straight line between the 2 points. Now, what would have been really good is if I'd actually labelled that A, B and C. Pretend it's labelled A, B and C. Pick any 3 points you like and just pretend. So we know that AC would be less than or equal to AB plus BC. But when we start talking about vectors then, well, the length of the side is the modulus. So I'm going to say Z1 plus Z2. So the modulus of Z1 plus Z2 must be less than or equal to modulus of Z1 plus the modulus of Z2. So we can prove that little result by simply using vectors and referring to the triangle. Of course, I could play around with that, and I could say, well, look, AC minus AB would be less than or equal to BC. So I could also say that the modulus of Z1 minus the modulus of Z2 must be less than or equal to. But notice I've done the absolute value of that, because when I'm doing subtraction, I might end up with a negative number. So I just want the length. Oh, when does it equal? When they all lie in a straight line, and we're not actually talking about a triangle. Here's a very old HSC question, 1995. We were presented with this diagram. It basically is what we just looked at, the triangle inequality. They want us to do it. Show that the magnitude of Z minus W is less than or equal to magnitude of Z plus the magnitude of W. So I'll join P and Q, and basically I'll just write down. Well, I know the length of OP would be the modulus of Z, length of OQ would be the modulus of W, and the length of PQ, well, I'll go Z minus W because I'll match what they've said in the question. And then I can say, well, look, by the triangle inequality, then this must be true. Part 2, construct the point R that would represent Z plus W. And then what can be said about that quadrilateral? So Z plus W, that'll be the other diagonal. So there it is up there at R. What can be said about the quadrilateral? Well, it's a parallelogram. Now, if those two diagonals are equal, that's what that's basically saying. If the magnitude of Z minus W is the same as the magnitude of Z plus W, so the two diagonals are equal, what can be said about W divided by Z? So we're saying the diagonals are equal. So we've got to think about it. What quadrilateral does it make it? Okay, it's a parallelogram, but I can now refine it down. If the diagonals are equal, then the shape I have is rectangle. So I now know it's a rectangle. That tells me that the vertex must be 90 degrees. So the argument of W minus the argument of Z must be, well, I've written in radians, but pi on 2 or 90 degrees. Now I'm going to use my rule about arguments. Argument of W divided by Z is pi on 2. If the complex number has an argument of pi on 2, then it must be purely imaginary. It must lie on the imaginary axis. Okay, multiplication. We saw this. Doesn't matter which order, but mod Z1, Z2 is equal to mod Z1 times mod Z2. And when it came to the arguments, we add the arguments. If I put that into mod arg form there, that's highlighting that we add the angles together. So this is where we get the idea of rotating. So if we multiply Z1 by Z2, the new vector that we create, Z1 will be rotated anti-clockwise by theta 2, and it's the length of the vector will be multiplied by whatever the length of R2 is. We've got two vectors there. A is Z1. I've rotated it by theta. Therefore, that new complex number B must be Z1 just simply times the cis of theta, because I have not changed the length of the vector. So I've multiplied by a modulus of 1, if you like. All I've done is added theta degrees to the argument. So that would be Z1 times Z theta. Now, if I change the length, then I would multiply by the factor of, or R, whatever the length is. That's really important. If you multiply by cos pi on 2 plus I sine pi on 2, it means multiplied by I. So every time you multiply by I, you rotate the vector 90 degrees. So IZ1 rotates 90 degrees. In fact, it's so important, I put it in a box. Let's have a look at this diagram. Now, it's a square, by the way. I didn't say it, but that's a square. We've been told D is the number 1, and A is some complex number omega. We want to work out what B and C are. So how can I get to them? So I'm saying, well, look, vector DC would be the vector dA rotated 90 degrees. So therefore, I must have multiplied it by I. And now dA, what is dA? It's not omega. Remember, head minus tail. So I've rotated omega minus 1. That's the vector I've rotated. So it'll be, but DC is not just the point C, it would be C minus 1, head minus tail. We're trying to work out what C is. So if I move the 1 to the other side, I could have left it, I suppose, as 1 plus omega minus 1I, because I haven't really split it up into real and imaginary, have I? Because I've got 1 minus I and the other one anyway, and we don't know what omega is, but anyway, something like that is what C is. Now, work out B. So from the point A, I'm going to add the vector DC. I'm going to just slide that up, and that will get me to B. So A is the point omega. To that point, I'm adding the vector DC. And DC, remember, C minus 1, which we worked out was omega minus 1I. Again, I've just played around with it. I probably could have left it as omega plus omega minus 1I. That one probably makes more sense. I've grouped the omega together. Now, of course, another way I could have done it. I could have said, well, to B, I'm going to add the vector dA to the point C. Well, the point C we worked out previously. So that's 1 minus I plus I omega. I'm going to add the vector dA, head minus tail, so I get omega minus 1. And if I play around with that, I get the same answer, you'll notice. So I could have done it that way. There's another way I could have done it. Have a look at this one. Remember, I'm trying to find point B. The vector dB, because I know this is a square, I've rotated the vector dA 45 degrees. But I've also changed its length. I remember the sides in a 45 degree isosceles triangle go in the ratio 1, 1, root 2. So I've multiplied its length by the square root of 2. So if I multiply the vector dA by the square root of 2, cis pi on 4, I should get the same answer again. Let's see what happens. So dB, head minus tail, B minus 1, is equal to the square root of 2, and I've actually written it as cos plus I sine, because I'm going to have to substitute in for that. And we're going to multiply that by dA, head minus tail, omega minus 1. Remember, cos of pi on 4, 45 degrees, 1 on root 2. That's nice because that'll cancel with the root 2 out the front. So I've ended up with 1 plus I, omega minus 1, plus 1 when I move the 1 from the other side. And rearranging all that, once again I come up with the same answer, which we would hope would happen. Yeah, so it doesn't matter which way you go, it's up to you. But there are different ways we could have found that point. 2000 HSC. We're told this shape is a rectangle. OC is twice the length of OA. A is the complex number omega. That's the only one they've told us. So the first thing they want us to work out is, what is C? So how do I get from A to C? So this one's going to be rotation again. If I rotate the vector OA, I'll end up, well, it won't be OC because I've got to change its length, but I'll be in that direction. We're told that length is twice. So if I multiply by 2i, so the vector OC will be OA times 2i, head minus tail, well in this case the tail's the origin, so we're just subtracting 0. So C will be 2i times omega. What complex number corresponds to the point of intersection D of the diagonals OB and AC? Well, I know diagonals bisect in a rectangle. So therefore, D is the midpoint of AC. I mean, it's also the midpoint of OB, but at this stage I don't know what B is. So it makes more sense to find the midpoint of the ones that I know. So midpoint of AC, but it's the midpoint, not the mid-vector, the midpoint. So from the point A plus the point C, divide by 2. And that's how we find midpoint. Substitute in, well we said A was omega, C is 2i omega, all of that divided by 2, and I've got a half plus I omega. That would be the point D. Some more examples. OAB, equilateral triangle. Side length 1, that makes it nice. And OBCD, that's a square. We need to find the points B, D and C. You know, when they ask you questions, sometimes they ask them in a certain way. You got to think to yourself, why didn't they say, find the points B, C and D? They said find B, D and C. Maybe they're giving me a hint as to which order to do this in. So, okay, let's find B. To get B, I'm going to rotate the vector OA, but this time, remember it's an equilateral triangle, we're rotating at 60 degrees, or pi on 3. So vector OA, well what's OA? Well that's just the number 1. We're told the side length is 1. So it's 1 times the cis of pi on 3, and cis of pi on 3 I can work out. So B is the point a half plus root 3 on 2i. Okay, we've got B. Now, I'm going to go for D next because I can continue the rotation. OB, I'm going to multiply it by I. So D will be I times the answer I just found for B. I get minus root 3 on 2 plus a half I. C we now have to work out. Well, that would be the point B plus the vector OD. So B we worked out up there. OD, well it's to the origin, so it's the same as the point D. I have my answer for C, 1 minus root 3 on 2 plus 1 plus root 3 on 2i. The points A and B corresponds to Z1 and Z2. Triangles OAP and OBQ are both right-angled isosceles triangles. Part I, explain why P corresponds to the complex number 1 plus I, Z1. Well, the vector AP would be the vector AO rotated 90 degrees, but this time I'm going clockwise instead of anti-clockwise. So that would be the cis of minus 90, which is negative I. So P minus A is minus I times O minus A. So P minus Z1, and moving the Z1 over, factorise, and there's how we get our 1 plus I times Z1. QB is going to equal BO times I. Okay, because I've got to find out what Q is. So part 2 probably should have been the question, what's Q, or something like that. So let's work it out. We're going to have to. So QB, that's going to be the vector BO, but this time we're rotating anti-clockwise. So cis of 90, which is I. So Q minus B will be I times O minus B. B minus IB, we get 1 minus I times Z2. So we now have Q, but we want to find M, which is the midpoint of PQ. So midpoint, it'll be the point P plus the point Q divided by 2. Adding them together, divide by 2. Well, there's not much more I can do with that really, because we don't know what Z1 and Z2 are. So Z1 plus Z2 plus Z1 minus Z2 over 2I. Whew! Told you that was going to be a long one.